Yo, yo! What's up, what's up, what's up? Advent of Code, day 8. We've been doing Advent of Code because it's fun, and we are doing it for fun. So, if we do something stupid, you can just assume that it's because it's the way that we want to solve the problem in the most fun way possible instead of trying to do like the most optimal or correct thing, you know? We're on day 8. We have gotten 2 stars on everything so far. Not like anything was particularly complicated. Day 1 and 6 had a couple hands, but everything else has been pretty straightforward. If I remember correctly, the lore is we are an elf and we are trying to make sure that the North Pole is shipping out all of its packages on time. Day 1, we had to break our way into the base by decoding a password. Day 2, we were doing some fix up of some database in the gift shop. Day 3, I think we went down an escalator. No, we fixed an escalator. Day 4, we went down the escalator into the printer area, optimized their workflows so that we could free up a forklift to bust through a wall to the cafeteria. In the cafeteria, we just like helped out our pals a little bit, figuring out what food was fresh. We go down, we fell in a trash chute and met up with some octopi, cephalopods, and we did cephalopod math. And then I think that the cephalopods helped us get, I don't remember where we went day 7. They helped us out of the trash compactor, and we were in the research ring. Right, and we had to help someone with some tachyon beam counting or something. I don't really remember why. What was the end state here? Did we escape? Maybe it doesn't say. Maybe we just keep walking. Day 8. We're in the playground. So we went through some teleporters. Right. The quantum physics stuff was because the teleporters had to get us to the right spot. So we got locked in a room. We fixed the teleporters, and now we get back in, and we end up somewhere else. We are in an underground space which contains a giant playground. Across the playground, a group of elves are working on setting up an ambitious Christmas decoration project. Through careful rigging, they've suspended a large number of small electrical junction boxes. Their plan is to connect the junction boxes with long strings of lights. Most of the junction boxes don't provide electricity. However, when 2 junction boxes are connected by a string of lights, electricity can pass between those 2 junction boxes. Okay, cool. Elves are trying to figure out which boxes to connect so that electricity can reach every box. They even have a list of all the boxes positioned in 3D space. Okay, so here we have probably XYZ coordinates in some unit that is undefined. This describes the position of the 20 junction boxes, 1 per line. Each position is given XYZ coords, so the first junction box in the list is at X162, Y817, blah, blah, blah. To save on string lights, the elves would like to focus on connecting pairs of junction boxes that are as close together as possible, according to straight line distance. Sure. By connecting these 2 junction boxes together, because electricity can flow between them, they become part of the same circuit. After connecting them, there's a single circuit which contains 2 junction boxes, and the remaining 18 junction boxes remain in their own individual circuits. Now, the 2 junction boxes which are close together, but aren't already directly connected, are these guys. Wait, why? After connecting them, oh, sure. Sorry, so nothing's connected right now? Did we not just connect these 2? Am I missing something? I thought we directly connected them here. In this example, the 2 junction boxes which are closest are these 2. By connecting these together, they become part of the same circuit. After connecting them, there's a single circuit which contains 2, and the remaining 18 are all on their own. After connecting them, I see. There is now, oh, these are different numbers. Sorry, these are different numbers. I see. There is now a single circuit with 3 and 17 remaining. My bad. I saw a 4 at the beginning. I was like, that's the same number. The next 2 ones that connect are these 2 bad boys, and there's a circuit containing 3 junction boxes, a circuit containing 2, and 15 circuits which contain 1. Okay. The next 2 are these guys, but they're already in the same circuit. This process continues for a while, and the elves are concerned that they don't have enough extension cables for all these circuits. They would like to know how big the circuits will be. After making the 10 shortest connections, there are 11 circuits. 1 circuit which contains 5 junction boxes, 1 which contains 4, and 2 circuits which contain 2. And 7 which each contain a single junction box. Multiplying together the size of the 3 largest circuits produces 40. 5, 4, 2. Your list contains many junction boxes. Connect together the 1,000 pairs of junction boxes, which are closest together. Afterwards, what do you get if you multiply together the sizes of the 3 largest circuits? Jesus Christ. Okay. I think I understand. So we are in 3D space. We can draw it as 2D space. We've got a lot of little guys together, and they're literally just saying, give us the, like, construct circuits by connecting pairs of these guys, right? So it's like, we connect these two, and then maybe we connect these two, and then maybe we see these two are close together, so this becomes a set like this, and then maybe this becomes a set like this. And they're basically saying, take the 1,000 closest pairs, connect them all together. What are the sizes of the circuits? So the question becomes, is like, what is like the efficient representation here? So I think that we don't, I was going to say we don't have a choice but to compare every set of points, but that's not true. That is not true because they are spatially located, right? So we've done problems like this before, like in the bus planner. I think we got somewhere very similar where you can kind of construct these like trees where you kind of like split up the inputs such that like you can keep bisecting the space so that you kind of have like a tree structure of like who's nearby you was what we did in that scenario. So I wonder if there's something we could do there, right? So you can kind of say like, because what we're trying to avoid is having to compare like this guy with this guy, right? These guys are obviously not the closest pair, right? There's a lot of guys that are closer. So some sort of like tree structure where you split, like you could do something where you like find a way to bisect, you know, something like this. I don't know if this is the play. I'm just drawing stuff to try to like freshen my brain up a little bit. But you could do something like this where you basically keep bisecting the space with a new plane. And maybe at each level of the tree, you are specifying the plane that you're using to bisect. That seems kind of hard if you allow arbitrary bisections. So maybe we simplify the problem by making them axis aligned. Right? So I think that you could do something where you alternate directions of bisection. Right? So you kind of say, let's draw like some points around like this or something. Right? So you kind of do like your vertical bisect here. Then like a horizontal bisect. Then in each of these quadrants, do you do it again? Is that what we're doing? Probably something like that. That helps you find the closest point to a certain point, but I don't think it helps much with finding the closest pair. It can, I think, if you at least know to like when you're looking at this guy, you can kind of go like up the tree, you know what I mean, and compare with your neighbors nearby. I guess that doesn't help though, because in this tree scenario, like if you have a guy here and here, these guys are not close by in the tree, right? Because we got to this point in the tree by going in here, then in here, then in here, right? So maybe this is not the solution. That's a quad tree. Oh, you're just I see. I see. But you could do something where you just the simple solution here is just grid it. Just grid it the fuck up. Right? So we can just choose a like resolution of a grid that we care about. right? And just kind of size this appropriately such that that elements are like somewhat evenly spread, maybe. And then each of these cells could have like buckets, right? So we could have something where we have like a lookup to say who is in this bucket, and then we could just check the buckets around us, right? And we could do kind of like a swirl, like a expanding search until we find nearby ones. You could do something where that's relatively okay. Can you use Manhattan Length to do initial grouping? I don't think that really helps us. I don't think. Another option here is if we were willing to do each comparison of distance once, you could use like a binary heap, right? Where you just say like, let me sort all pairs by distance and just let me keep popping the top one. Interesting. But to find this closest pair, you'd have to do this in each point and not just one point. That's also true, right? So I was imagining the scenario where you're trying to query which point is closest for each point. And so, like, without any sort of like intelligent spatial reduction of this problem, you're kind of just forcing yourself to compare every point with every point. And I was trying to say, at least we can reduce the problem such that for every point you only have to compare with a smaller amount of points, right? But I guess like with this grid problem, you're making the trade-off where if like your points are clustered like this, right? To find the closest neighbor to this point, you have to search all of these like empty spaces now, right? Which like does increase cost in some way, which is kind of funny. I need to look at the problem statement again, because I'm not 100% sure which problem we're trying to solve yet. So we are trying. What was it? It was 1,000 closest pairs of junction boxes, right? So I'm assuming that means that there's a lot more than 1,000. Like, how big is this list? That's the first question to answer, I think. Day 8 input. Okay. Can we just do a little day 8 input? There's only 1,000 inputs. Okay, so this means that we need to look at the very least every single. Wait, is that true? If there are 1,000 pairs for 1,000 inputs, I guess you have to look at. I guess the amount of connections in this is 1,000 squared, right? That's the amount of connections that there are. Okay, so we are limiting it by 1,000 factorial. Yeah, I guess because they're bidirectional. Yeah. You are right, because once you've hooked up 900, I think that's right. I think 1,000 factorial, not. No, wait. No, 1,000 squared. I'm back to 1,000 squared. 1,000 factorial is bigger. Sorry, it might be like 1,000 plus 999 plus 998 plus 997, which is not factorial, but it might be something like that. Okay, so we are looking at a much smaller subset, like around the square root of possible connections. It would also be interesting to look at like the distribution of these guys. That might help us a little bit as well. Okay. I'm just trying to think about like how do I want to solve this problem? Maybe the first thing we do is render these guys somehow, just so that we can get a feel for what the distribution looks like. And then we can start thinking about how do we write a data structure which solves that effectively, I guess. So how do I want to do this? What is the easiest way to look at dots? I guess we probably can just render this into a ppm. That's probably the easiest way right now. Okay, let's do this. So this is a lot of thinking. Let's like actually write some code. Visualize, maybe. So let's do current working directory, open file, day 8 input. And we will do, reader buff, you know, we have a reader here. While reader, while true, I guess, it's like reader interface, take delimiter, we're looking for a new line. We have an error, which could happen. Sometimes that's end of file. So if it is error end of stream, we break. Else we return the error because it's an actual error that we can't handle. This is the row. We say index of, I guess, like split scalar on comma. And we're like x is this guy, yz, and these are the strings versions of these guys. So now, oh fuck, it's 3D. That's okay. I think. I guess if it's 3D, we want to export a file that we can look at in Blender, huh? Let's do that. Wait, like obj file format. Can we just huck a bunch of these somewhere? Is that like a thing we can do? I guess we'll find out. Okay, so can we don't even need to parse these yet, right? I guess they need to be I guess let's just see what happens if we just write these directly into an output. Obj out is create file data obj. Boom, day 8, I guess. Can we do something like obj out? I guess we need to put right try here, and we need a like writer buff as well. Writer is f out obj out writer with writer buff. Here we're probably doing something like try writer interface flush. Here we are writing out you know, something like v with a bunch of strings, which are just the x, y, and z positions. And then can we run that shit? And then day 8 obj, is this, we forgot new lines. Okay, do you think this is something that we can open in Blender? We'll find out. We will find out. Nope. Not open, sorry, import. Import an obj file from this guy. Okay. Bad news bears. This doesn't look promising. Okay. Can we try something? Okay, I want to try something more intentional. Okay, let's just do this and import that and just see if we can actually see anything. You know what I mean? Like, is this a valid object? Yes, we can actually see the vertices here. It's probably just that the scale of these vertices in the thing that we exported before was like too high. So let's do this. Let's start by ripping the file. We'll rip the file twice, I guess. And we'll get like the scale. You know what I mean? So can we do something like this? Let's do a chord iter. So this guy is gonna have a reader. And here we go next, and we get a chord. Chord is a struct, which we will give him 3 floats. We might regret this being floats, actually. We should probably do this as... are they unsigned or signed? Looks unsigned. I think we'll do U63s here so that we can easily cast to I64s. Maybe we just do I64s directly like this, actually. Because I think that'll be more convenient. And can we do something like, say, this guy, he gets a row, and this is now return null. And then he kind of has this code, comes up into the iterator, and then we say return. This thing is failable because parsing could go wrong, and also because reading could go wrong. And then he says, you know, X is try std format parse int into an I64 of the X string in base 10, and we throw these around a couple times like this, bang, bang, boom. So now we can rip this file twice. So we can say, is chord iter reader is reader, right? We can do while iterator next. And we can say scale. Maybe like this. And then we say scale is the maximum of chord X, probably absolute, right? And the scale like this. Okay. And then we do it again. So we say like reader seek to 0. And then we go while IT next again. We say X is chord X, probably like this. Float from int of chord X, and then we say X divide equals float from int scale. Maybe we want these as F64s because they're big numbers. And then we do X, Y, Z. Like this, like this, like this. And then we have X, Y, Z here. And maybe this looks a little bit more reasonable. Oh, maybe I need to actually run the code I'm trying to run. No field interface here because we have the interface already. I64 and U64 somewhere at 46. God damn it, dude. It's fine. Aaron union is ignored here. Bing, bang, boom. Cannot assign to constant. So true. And there we go. Can we open the file now? Delete, delete. Import, obj. Let's take a little peek skis. Nice, dude. That's pretty, I would say, uniformly distributed. right? So that gives us some clues about how we want to implement. Right? It's not like Gaussian distribution in the middle, right? Like we're not seeing like a big cluster in the center. Right? I think these guys are relatively uniformly distributed. I don't know what to do with that information necessarily, but that is like there's something with that. Solve the problem with the Blender node editor. Fucking kill me. I would never. I did a lot of work with the Blender node editor at some point. And that thing's a pain in the ass. Even more funny, I actually wanted to write code that generated node graphs in the Blender. So that code's even funnier because you have to generate Python code to manipulate the UI to create, like, doing something like an add is like you create the two add nodes in the graph and then stitch the connections together. And so trying to do anything there is like a disaster. How many subs to solve in Blender? Money doesn't influence me like that, so probably like no amount. Is OBJ format open source? You just have to know some format that works. We've just looked at the OBJ format before. OBJ file format. I don't really know where this is. Just from some program, I guess, and it's just like simple. Perfect. I've just donated none subs. Perfect. Okay. So I suspect that the grid answer is probably a relatively good solution here, right? Because if you were to split this up into like a 10 by 10 by 10 grid, you'd have a pretty good you'd have a pretty good chance that the thing you're trying to look at would be in there. So maybe we do that. There's another part of me that wants to write a binary heap right now anyways, because it's going to be useful in something else I'm going to be doing like soon. But I do like the grid idea best. Maybe we do both and compare. Maybe. But we'll say grid approach first. We will do the grid approach first. So, I guess, what are we going to do? We are going to take each point as we iterate, and we are going to plop it into a cell in a grid. Is 10 by 10 too big? 10 by 10 by 10. If things are evenly distributed, that's how many points per cell. 10 times 10 times 10 is 1,000, so that's too small, right? Because there's 1,000 points. We want there to be kind of like somewhat. We want there to be a good chance that there's someone close by. So maybe a 5 by 5 by 5 grid is better. Isn't priority queue a heap? Oh, does it exist? Oh, it does exist. Wait, so we can write the dumb version? Oh, hell yeah. Wait, that's sick. I didn't know it existed. Perfect. So I don't have to write one. In that case, why don't we do both then? I've changed my mind. We do, well, yeah, we'll do the grid approach first, and then we can compare with the priority queue approach. And we can see how much faster it is, which is a fun little game to play. Okay, so we have what? What is our storage format in here? We want to go bi-directional, right? We want like points. Maybe not. So maybe it's like a cool, like we have, maybe it's just like grid is a 125 thing where each cell can have like, I guess, like this, right? Maybe linked list is like nicer here in some way. Maybe slices here. Maybe that's fine. Maybe that's fine. So to construct the grid, I guess we'll kind of store it like this. Yeah, fuck it. I guess we'll call it cells is a better name for this, right? So as we're building this, these are going to be array lists of chord, and then we'll kind of convert them at the end, I think. Let's just be really like fucking cheeky with our allocators, and we'll just be like fixed buffer allocator, and we'll just try to size this so that we don't ever have to free anything, and we'll just leak like crazy. I think that's probably fine. Page allocator alloc, and can we just allocate like a meg? That's surely enough. Surely enough. Surely. Okay. So this guy is like, yo, I got a grid builder. Here's a chord. And we're like, I guess we have to have some function that's like, get like cell num, get cell. What's the thing here? We had like a chord. And we probably want like scale as well, right? I think. Because we need to normalize this to the maximum size. I think. I don't know, man. And how does this work again? It's like I guess it's like cell like what's the word for like divisions along a single axis? Like what is 5 here? Axis len, I guess. So then this is like cell, like grid size is cell axis len times cell axis len times cell axis len. Stride, yeah, I guess that is a grid stride. I agree. I like that better. Boom, here and here. Okay. So what is this? This is like it's chord x out of scale times grid stride, I think, right? And then you have to invert this for integer math. So here we have this where we get our x, y, and z positions, and then the coordinate is z times grid stride times grid stride plus y times grid stride plus x, right? I think it's like something like this. Something like this. Pretty sure. Pretty sure. We got to be careful about maximums here, right? So if the scale picked the maximum value, which means that we're gonna cap out at 1.0. So you might want to do scale plus 1 here, I think, just to like fix the boundary condition. I'm not 100% sure about this. So we could do get cell here, right? So if we're like get cell you know, if we have like x is 0, y is 0, z is 0 from with scale of like anything, this should be 0, right? So this is 0. And then if we are going to 10,000, this should be like maximum y 0, 0, right? So this should be, I guess, like x is obvious. This should be 5. And then this should be like this, and then no, this is I'm confused now. I'm confused because this is my maximum value. So how is it possible? I guess because I can't ever be 10,000. I guess that's the problem. Yeah. So I'm expecting, I guess, -1 here if we're all the way up, right? So if we're at like 9999, I guess even 10,000. 10,000, 10,000, 10,000 should be the last element, which means that all these are probably off by 1 somehow, right? So this would be grid stride -1, -1 here, maybe minus grid stride. I'm not really sure. Not 100% sure. Zig test day 8. Hold on. We gotta get this shit compiling again. Scale here. Whoa, what's happening here? I64 and U64. Yeah, I mean, I guess that's true. Can we... I mean, our chords just be U64, right? Why did we make this I64? Okay, so this passes, which makes sense. Then this one is also the obvious. Like, the maximum value everywhere should be off by 1. And then these ones I'm a little less sure about. So I guess this is probably minus grid stride here. Yep. I just want to make sure that we are actually testing something. Yep. Okay. And then this one is minus grid stride squared, I guess. Yeah, okay. Indexing looks about right. So now when we are building this grid, we can say, yo, self cells at get cell for the coordinate and the stride, or yeah, so, or I guess the scale, which means we probably have scale here, right? Append with our allocator and the chord. Boom. Easy. Easy peasy. And then finish is gonna be like, I have a grid builder and I want to get my grid out of this bad boy. Right? And he's like, it's literally just, it might be easier if this is like this, to be honest. I guess maybe a pointer to this thing. Is that the play? Because I don't really know, maybe it's fine. I don't really know like what the Zig rules are if you return like a big array like this, right? Like, if it's like a... You kind of have to go like this, right? And you have to go like 4 ret cells. Oopsies, this should be... Why does he think this is 5? Like, we kind of want to do, like, cell is equal to self cells. Like, from is going to be, like, from items, right? Easy. And I don't really know. This is, like, kind of stupid, right? In terms of, like, performance. If this was already heap allocated, then, like, we wouldn't have to copy-paste this whole thing. So maybe that's better, but, like, whatever. Okay. So now we are going to have this, like, builder. Who gets his stuff from, you know, around. Scale is scale, easy, and cells is splat array list chord empty. Okay, so then as we read these things, we're like, yo, let's fucking huck up these things in here. Push chord, easy peasy. And does this run? This guy needs to be variable, not constant. So true. And we do need to write try here. And then can we just quickly write the cell counts? For builder, I guess we have like grid is builder finish. And for grid cells, cell, can we print the index of the cell maybe? And the count? Or something? Like how many things are in each of these? Yeah, nice. Nice! Nice! Okay. So we could actually drop this a little bit, to be honest. That feels a little better. Those are all like single digit numbers. And then does our test still work? Look at that. Look at that. Okay. So now what we want to do is we want on grid, we want to be able to be like get closest point. And I almost want each chord to be like an index into some like I almost want like our coordinates to have like IDs, because then you can kind of loop over all of your coordinates and then get the closest by ID. Right, because like we right now don't have like a comparison for like, is this the same fucking point? You know what I mean? Yeah, so can we do this? Yeah, so here we're actually gonna say like chords append chord. We have like, this is the index, and here we're appending the index here instead. Can you just number them? I think that's what I'm doing. I think. Can't you just compare the coordinates? I don't know if we have a guarantee that two won't have the exact same position. I don't know if we have like a uniqueness guarantee. So if there are 2 points that are directly on top of each other, we need to count those as a pair. You know what I mean? Like that's actually like the most important case, almost. Like that's like the best junction box. Like maybe that's not the case, but I'm not like 100%, so I'd rather just do it this way. You know? You know? So core, then I guess it's like, this is better if we do it like this. Cells is undefined, but chords is just like this list directly. They never cover. Check. They never cover. I check tested it. For your input, my input might be different. There are circuit boxes, unless we consider the multiverse like in day 7 problem, then I don't think they can exist in the same place. That's a good point. It really depends on the resolution of the locations, right? Like if your unit was like in meters or something, right? You could have 2 boxes within a meter of each other within like, and you might have like, maybe they're not uniquely identifiable. I don't know. I would just rather solve it this way, because it's like just I think that the cost here is minor, and the like it's easy to do it this way. You know what I mean? Is what I'm trying to say. like just one little extra indirection is easy. It's easy to solve the problem, is all I'm trying to say. Wait, why is he pissed about? I guess we need Alec here. After calculating distances, you don't need to remember position. But I'm not calculating distances. I'm not calculating distances between every pair. So like I'm trying to see if by doing a spatial lookup, do we get a better, do we calculate the answer faster, is what I'm trying to figure out. Okay. So here, I think we want to go get closest. Oh, fuck me. I didn't think this all the way through. That's funny. That's funny. Because I didn't consider the fact that... Oh, I'm a dumbass. Okay, so I was thinking for each point, you would only you would compare each point to like the next point. But I actually have to compare this with like all of the points nearby. Not necessarily all points in existence, but to all points nearby, right? Because this guy is probably closest to many, like, how do I say this? It's not like I have a guarantee that we're going to use every point. You know what I mean? So I was initially going to loop over every point and check who's close by. But that's obviously not going to work. So it's almost like, yeah, this might be a stupid fucking solution to the problem. This might be a stupid fucking solution. Because how do I say get closest pair? Right? Which would kind of give me like this, right? I think that you would have to do like get closest pair. You would have to like loop over all chords and then do like get close, like get, yeah, this is fucked. This is fucked. I was, fuck. I guess we could have a distance threshold and then this is still relevant. Right? Like the thing that like, yeah, if you have enough pairs under some threshold, this is still helpful. Because what I'm trying to avoid, or what I was initially trying to avoid, is the idea that I'm comparing this guy with this guy. Right? This is so fucking stupid in my brain because it's like that will never fucking happen. Right? That's never going to be relevant. We only need to find the closest, what is it? Like 1,000 out of million connections. Right? And so I think this does still help. Right? We just need to find an appropriate size here. So if these points are evenly distributed, like we probably only have to look. There's probably some calculatable distance that they should fall under. Yes. Yes. So, and it's probably something related to, I don't know. I don't know. It's I bet you there's a square root involved in here. There's some statistics that you have to do, right? Where it's like Yeah. I don't know the math for this, and I don't really want to figure it out. So what I'm going to do is I'm going to uh threshold this. So I'm gonna say like give me like a pair iter here, and I'm going to say that I have some like max distance. And we can actually do this in cells. Yeah. Okay, let's do this. I think there's a good chance, by the way, that whatever we end up with is slower than just doing the heat. So it's going to be fun to compare at the end if we actually win. Because I think that there's a good chance that the answer is that we don't win. But we'll see. Okay. So max dist cells is going to be stored in here. And I guess we are going to do... Oh, is an iterator the right way here? This might be a bit of a pain. Because we have... I guess it's fine. So we're going to have my source cell index, which cell we're in, then like source cell sub index, right? So this uniquely identifies one point. Then we have a dest cell index and dest cell sub index. Yes. And as I guess like we define like a wrapping order here, right? So we define like I need to draw it in 2D. I need to like look at it in 2D first. But right, so like if we are looking at like this, say our like max distance is 1 unit away, which we could actually just size the grid such that 1 unit away is fair game. Maybe that's what we do. Is we just we only look at the adjacent cells. Yeah, let's do that. Let's do that. Fuck this max distance cells. We'll just size our grid such that the problem is solved correctly. I like that. So that way, all we have to do is say this is index 0. Then we do like 1, 2, 3, 4, 5, 6, 7, 8 or something, right? But for a cube, it's different. So it's we in a cube have, what is it? It's 10 cells to look at, I think, probably. Right? So we have like our 1 in the middle and then like 9 around, right? Because it's I guess it's actually 27 probably. There's 3 here, then 3 here, and 3 here. So it is 27. 3 by 3 by 3. So I guess we do something like, maybe it's easiest if we just define like x offs is self, I don't know yet. Oops. Hold on. This is giving us a probably this. Right, so a pair of points and their distance is probably what's coming out of this thing. And this is like dest cell index Mod 9? No. So we want this to be like the inner loop. So yes, then this is mod 3 over 3 or something for Y. And then Z is over 9, I think. So. This will give me no. Should be 3. And then %9 over 3. No. Hold on, I'm thinking. So we want this to go like 0, 1, 2, 0, 1, 2, 0, 1, 2 for X. Then for Y, we want this to go 0, 0, 0, 1, 1, 1, 2, 2, 2, 0, 0, 0, 1, 1, 1, 2, 2, 2. And then for Z, we want this to go 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1. So 0. So this has to be over 9. Great. Then this is divided by 3 mod 3, I think. Right? Is that right? So this goes 0, 1, 2, 0, 1, 2, 0, 1, 2. This goes 0, 0, 0, 1, 1, 1, 2, 2, 2, 0, 0, 0, 1, 1, 1, 2, 2, 2. Yeah, okay, cool. Okay. But then these are not offset anymore. So this is just easier if I store these like this. No, it's not. I don't know. So yeah, then I want these to be like integers in some way. I don't know. I haven't figured it out yet. So I want these to be like -1 to 1 almost, right? That's kind of what I'm thinking here. So this is gonna be 0, 1, 2, so this has to be subtracted by 1. Okay. So this gives me 0, 1, 2 for each of these guys. Then what? Then what? We need to like take our cell position here. So we want to go like, can we get like, we have like get cell. Can we like get cell neighbor? So this is going to be our cell index. And we're gonna look at the X offs, Y offs, and Z offs. Right? And we have to be like, our grid X is cell index % grid stride. Our Y index is cell index divided by grid stride mods grid stride. Right? And our grid Y is cell index over grid stride, I think. Not really sure yet. And so then we do grid Z. I guess this thing can return null. So if grid, can we convert these to like I32s or something? And then do int cast on these. And then do like if grid X plus X offs is less than 0, or I guess like can we do this? Maybe we do this, and then we do grid X plus equals X offset here. Yeah, something like this. Something like this, right? Then we say like if grid X is less than 0 or grid X is greater than or equal to grid stride, return null. And we do this for all 3 axes, I think. Then we just return this with an incast, probably. I think that's right. Maybe. Maybe. Get cell neighbor. So here we want to be like I guess we can do something like this. We can go I want to test like I guess it doesn't matter. So we can do can we write a quick helper function? Get cell neighbor test helper. Hear me out, hear me out. So I want to give it like X as a U32, Y as a U32, Z as a U32, X offs as an I32 or an I8, Y offs as an I8, and Z offs as an I8. And we should be able to go like get cell from XYZ, right? And I guess we need stride in here as well. Or scale, I mean, was what it was called, not stride. And then I want to do get cell again of with the offset applied. Which is gonna be a pain in my fucking ass. So what I'm gonna do is I'm actually gonna take these as I32s, I think, and cast them here. I think this will be simpler. And this is like dest cell index is plus X offs plus Y offs plus Z offs here. We need to check, I guess, if we're on the border, which is not helpful. Fuck. God damn it. I guess maybe we just do it manually. I'm not sure. Let's write one. Okay. Get cell of X equals 10. Whoa, hold on. Hold on. Oof. Okay. We need. It's fine. It's fine. Get cell neighbor. Oh god. I think we need like cell index from cell XYZ or something. Yeah. We do need this. Which does this. Okay, grid X, U size, grid Y, U size, grid Z, U size. Okay. Jesus Christ. Okay, so now we can do cell index from grid XYZ with like 0, 0, 0, right? Maybe we do 1, 1, 0 or something. And we say we are expecting I don't know, man. Expect equal. Okay, so if I go like offset in some way here on Z, Get cell neighbor. Okay, here we go. Here we go. So 0 at x, like -1, -1, -1 here. This should give me null because we're going out of range on z. Yeah, it's like something like that. Jesus Christ. Okay, cool. Now we can start doing this. So if we go offset 0, we should be expecting the same thing here, right? If we go 0 offset, wonderful. We'll just change something to make sure that we fail correctly if we fail. Nice. And let's try to kind of just start writing out a couple test cases. I think this is probably how I want this formatted. Yeah, something like this. Okay. So, if we are at 0, 0, 1, 0, 1, 0, and we're going offset from -1, I want to see 0, 0, 0. If we are going at grid stride -1 in each dimension here, and then we do -1 in each direction, I want to be seeing grid stride -2 in each direction or something. Oh, oopsies. Backwards. Maybe like this. Oopsies. Oops, doing something wrong here. This is at 83. Okay, so this is bad. That's bad. So here we were supposed to get... What the fuck? Okay, so we have 0, 1, 0. What is our cell index? Um, 8, 8, 0. The fact that these are the same is concerning. Right? Oh, 8, 8. Sorry, no, that's right. 8, 8. Oh my god. We gotta comment some stuff out. I'm too stupid. Okay, cell index 0 in get cell neighbor. Oh yeah, my bad. I've got the fucking expectation backwards. Oopies. Oopies. Much better. Okay, there we go. God, fucking tests are so hard, man. Okay, let's put test on like the right side now. So on any of these +1, this should be null. Beautiful. And this should also be null. And this should also be null. All right, cool. I think that's we've probably got it right. Probably. Okay, so we want get cell neighbor. Oh, oops. Here, these are all zeros. Okay. Why is this guy mad? Duplicate field? Hello? What do you mean duplicate? Oh. I see. I guess he probably needs this guy as well. I don't know. We're really flying by the seat of our pants here. Okay. So, we now have our offsets, and we can do something like get cell neighbor for source cell index x offs, y offs, z offs. Okay. This is a bad name. This should be like sibling cell. It's fine. It's fine. Note, this is adjacent grid cell in range of 0 to 27, not the index in cells. All right. So then we have, you know, cells at neighbor cell. I guess, like, we probably want to do something like, if, while what? This is like desk cell index is less than 27, probably. Less than or equal to? Probably less than. Probably less than. Here we do something like, if we don't find a neighbor, we do self desk cell index plus equals 1, and then continue. Great. Now we have a neighbor cell. If the sub index is greater than the cell length, okay, this is neighbor cell index, I guess. Howdy, neighbor. Howdy. If this is greater than neighbor cell len or equal to, we move on to the next cell, I guess. Right? Okay, and then otherwise we have our neighbor, or like our test. So we have like other point is oh, fuck me, dude. We're gonna get every point twice. We're gonna get every point twice. We only need to compare in one direction. I think. It's something like that where, like, in 2 dimensions, if I am, like, say we have, like, cells like this, right? And I am here. Like, if I have checked from this point to this point, I don't need to check backwards this way, right? So I think within a cell, we only check people to... I guess within a cell, we do have to check everyone, but we just don't... We discard points if it's above or to the left. And then we only check neighbor cells that are down and to the right or something. Ew. 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 Dude, we're so committed. We're sunk cost fallacying the fuck out of this. Random non-program question. Are you doing the Expedition Arc Raiders? That 5 mil currency requirement? Yeah, I mean, I have 2.5 mil right now, and I haven't really been trying for it. So I'm not really worried about it. I'll have 5 mil by the time we go. Because I think we have like a week, right? Or 2 weeks almost? Yeah, or like a week and a half. I'll have 5 mil by then. Yeah. I have 150k. I'm cooked. Yeah. Yeah, I guess here this now goes down a power, right? This is 8. This is 2, 2, 2, 4 here. And now our offsets can actually be U8s. And these don't get offset anymore. Right, so this should be 0, 1, 0, 1, 0, 1. Then I compare my other point. So this is a neighbor cell at dest cell subindex. And then, so I think it's like, if other point dot x is greater than my point is parent cells at source cell index sub index. Something like this. Or other point dot y is greater than my point dot y, or other point dot z is greater than my point dot z. Or maybe less. Yeah, because I'm trying to compare forwards, I guess. Something like this. Jesus Christ, I've made this problem hard for myself. Can't wait for another I may have overcooked this one video. Do we just give up? Do we just give up? Is this like not worth it? It's an hour 20. Like, are we gonna finish this in like a reasonable amount of time? Maybe not. Maybe not. But we'll see. Maybe we just keep going a little bit. Maybe we finish a little bit and then get mad and then give up. How about that? Just try the heap. I mean, the heap one I'm not even worried about. Like the heap we can do in like 5 minutes. So we're going to do that one either way to check our answer. But this is fun. This is fun. Okay. Continue and this probably. If dest cell subindex is greater than oh, we already have that check here. Oh my lord. Okay. Dist from self chord to other chord. We return it's a squared plus b squared equals c squared, but in 3 dimensions, right? So it's like x dist. Can we do these as U63s so that we can easily cast U64 or I64s? I think that's easier. And let's do F64 here. Or we can do dist squared, and then we can leave this in integer space, which is nice. I think. Yeah. Yeah. So can we do I don't know, man. Maybe I want to do this. I60 as I64. Val I60 U63. There we go. Something like this. Okay, so then we can do as I64, I guess xdist squared. Xdist is absolute value of as I64 self x minus as I64 other x. Okay, something like this. And then we can do something like return xdist times xdist plus ydist times ydist plus zdist times zdist. Okay, so now we can return this as U64, and then it's like return other point dist to my point or something. Oh my god. My point index is, or my point is self parent chords my point index. If my point index is equal to other point index, I guess that goes here. Bum, 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 bum. Jesus Christ. Ow! Ow! What have we done, dude? Ow! And this is actually, supposed to be like, my point index. No. Yes? Other point index. I think it's like this. Ow! And then we have to increment our source index as well. Ow. Ow. I don't want to do this anymore, man. I don't want to do it anymore. I don't need the ASCII squaring. Yeah, that's true. I don't want to do this anymore. I don't want to do this anymore. We're fucking... Fuck this grid, dude. Fuck the grid. Boo grid. Why did I do this to myself? I've decided. I've changed my mind. This is too much fucking work. It's not worth it. It's not worth it. It's just not fucking worth it. We need to know when to call it. We're doing the fucking heap, man. We're doing the fucking heap. Okay, how do we do that? We have to compare all points with all other points. So, I gave up on my grid attempt way faster than you did this morning. Hell yeah. Okay. So, what do we do here? We buffer all of these in an array. While iterator next, we have some chord, and we say chords append chord. 4 0 to chords items len a. Maybe it's like this. That's fine. A index 4 a index plus 1 to chords items len. This is probably -1 here for that +1 to work out. B index. We have A is chords items at A index. We have B is B chords items at B index. We have some sort of heap stood priority queue. I've never used this thing before. So what is this going to be? How does this thing work? Priority queue for storing generic data. Initialize with init provide compare function that returns order less than when its second argument should get popped before its third element. Sure, so this is like, I guess we're looking at pairs, right? So I guess we have like a chord pair. Who's gonna have A, B, and their dist. Dist squared, probably, right? So here we have our context is going to be our slice of chord, I think. And our compare function, compare chord pair. So he's gonna have a context of chords. He's going to have A chord pair, B chord pair, and I guess he doesn't actually need a this is context of void actually. And this stood math order, I think is what we're supposed to return here. And it's literally return like A dist 2 and B dist 2. Okay. So it's literally Q is this guy. Do we need anything else? No. And then does this guy need to be like initialized or what? Yeah. This is Q add. Nice. A is A index, B is B index, and dist2 is A dist2B. Easy peasy. Then what do we do with this guy? What do we do with this guy now? It's like we keep popping from the queue. So for 0 to 1,000, we're doing like queue remove. Okay. But for the test, the example, which we're gonna have to look at, we'll get there. We remove a pair, and so then what are we're fucking putting these in sets now? Yeah, so I guess we need to list all the sets as well. So we need like a lookup from like index to set ID, and then yeah. So set lookup is auto hash map from usize to usize. And then I think our sets, I think, is just again a lookup from this. Like, so I think that we like, I don't think we need to keep track of this is like set count, set size, I guess. I think it's like something like this. Next set ID is something like this. And so I think it's like here we check like it A is set lookup get or put alloc A index, and then we do the same with B. And if they're both not found, like if they're both not found, we initialize them both. I guess we have like the set ID here is set I don't know yet. It's like next set ID plus equals 1 for sure. I guess this set size thing could be an array. So it's like here we have like set size append 0. Yeah. Yeah. This is the play. Set ID is set size items len here, and then we're like set size. I guess it's append 2. Right? After making the 10 shortest connections, there are 11 circuits. We're trying to multiply the size of the 3 largest circuits. 3 largest circuits. Oh, gross. Ew. We'll get there. Holy fuck, dude. This is like 10 times harder than any of the other Advent of codes. What the fuck? Okay. Then we have like set lookup, put a this guy, and B gets this guy. Right? That's easy. Then else if B got found existing, we look at A's. Oh, we have to initialize these too, right? Wait. Yeah, we don't. It's like this. My bad. Okay, and then set size at here must be plus equal to 1. Okay. Okay, and then else if A got found existing, we do the other way, right? So it's like we take B and we assign it to A. It's probably like something like this. Holy shit, dude. Okay, so let's start this with how many connections are we making in the example? 10. So does this work with the example input right now? So after this, we should be able to iterate over set size items, and we should be able to print the set size. Let's just see where this gets us. Day 8, input, example. All right, jeez Louise, man. While IT next, we need to write try somewhere probably. Chords append needs an alloc here. Okay, so we have 43222. Is that what they got? After making the 10 shortest connections, there are 11 circuits. 1 which contains 5, 1 which contains 4, and 2 which contain 2. So no, we fucked this up somehow already. Can we write down what the pair is? pair of this guy and this guy. So this is chords at pair A and chords at pair B. Okay. So we do see 162, 817, 812 here, and 425, 690, 689. Great. Now we get 162, 817, 812, and 431, 825, 988. Okay, so we're at least doing that right. We're at least getting those. And then we get 906, 360, and 805, 96. Beautiful. Oh, we already have to check if they're in the same circuit. Which we are. We're missing something here. It's like. Else if A got. Oh, we need to merge, right? Else if A got value pointer is equal to B got is not equal got value pointer. We need to like merge sets, right? So it's like. Oh my lord. We need to merge the groups, which is not trivial with what we've set up here, right? So we need set items here. Is that true? Is there an easy way? Jeez Louise. Alright, we're just getting fucking stupid with it. It's fine. Okay, so if we're just gonna keep all of the IDs in here. Set ID is set items, items len. Here we are appending an empty thing, and then set items at set ID. We're inserting A and B. Okay. Then here it's set items this guy append B, and then this is append A. And then so if theirs are not the same, then we need to like nuke a set. So for now, instead of doing anything intelligent, I think we will just say a got value pointer. No. Set items at A. Append the slice from B gop. Like this. And then can we just do like clear B? And then for set items, can we do items len or something? Oh my god, dude. Holy moly. Probably need some tries scattered around here. Forgot a pointer dereference over here. Append slice also needs an alloc. Holy fucking hell, dude. Oh my god, alloc here. Forgot to change BGOP to ABOP. I think it's okay. Everything looks about right. I think. Adam, thanks for the raid. What's up, you guys? What is up, you guys? We are doing Advent of Code, and we heavily underestimated how hard it would be. Heavily. So we are in this problem where we're trying to find in a cube of data. Here is our cube of data. Find the 1,000 closest points together, or the 1,000 closest pairs, and in there we have to, I think, connect the 1,000 closest pairs together over and over again. So take each pair in the 1,000 closest pairs, connect them, then find the size of the sets that we made by doing that, and then multiply the top 3 sets together or something like that. Something like that. We have 5, 4, 2 that contain 2. So that is correct here now. We have 5, 4, 2, 2. We've left 1 behind in our implementation, but fuck it, I don't care anymore. I don't care. We've been doing this for too fucking long. This question's way harder than I expected it to be. I don't fucking care. So now what we have to do is we need to find the largest 3 sets. Anyways, thanks for the raid, Adam. Hope you all had fun over there. We're just gonna keep ripping through because I want to fucking slam my head through my desk. So we have to finish. Alec here sounds like the Thunder Fury Blessed Blade of the Windseeker. Did my joke even make sense? I'm fuzzy on WoW lore. I was never a WoW guy, so I don't know. Okay, fuck. What are we doing? We want to loop over these things and find the biggest 3. And I'm tired of trying to do something smart. Max 3. Max is 3 U sizes, probably. Mark or something. With a value. And this guy's gonna be like 4 self maxes. Max, if size is greater than max equals size and break. There we go. Surely it's something like that. Max 3 is a max 3 initialized with maxes of 0, maybe 1. Right? Because there will always be 3 1s in there, probably. So then we're like max 3 mark with items len, probably. And then can we go for max 3 maxes? Max debug print max this. Please God. 247. He's mad because I didn't put an ampersand here. 5, 1, and 1. Bad news bears. Why? Oh, because the break isn't in the if, because I'm a dumb fucking idiot. There we go. 5, 2, and 2, that's still wrong, right? Should be a 4 in there somewhere. What am I missing? So we do have 4, 5, oh. I see, because we need to fucking take the minimum of the maximums. I guess what we can do here is size is size in. And we pop it out. Can we do swap here? And then we'll just kind of swap our way down to the end. Something like that. You know what I mean? There we go. 5, 4, and 2. 5, 4, and 2. I'd just slap a sort on there somewhere and call it a day. Yeah, that's probably fine as well. Okay, and then we do stood debug print total is this. So max 3, max is 0, times max 3, max is 1, times max 3, max is 2. And then we got 40, which is their answer, and now we have to do the same thing with the real input. So bring this back up to 10,000, or 1,000, sorry, and bring, what was it? Somewhere we want the right input. Day 8 input. Out of memory. That makes sense. We're just gonna go crazy with it. Fuck it. 10 megs. Wow, really? Crazy. Let's see if we got this right. Fuck! No! We got it wrong! We got it wrong! Shit. Shit. Okay. How do we debug this absolute fucking disaster, dude? How do we debug this? What's my strategy? We find the 1,000 closest pairs by shoving them in a heap. Then try to group them with a couple array, like a how do I say this? Array and a hash map where we say which set ID are we in. I think we need to get a little bit more intelligent with these. How confident we are in that max method? Probably not that much. Yeah, I'm kind of down to throw a sort on there. I am kind of down. I mean, that looks right to me. That does look right to me, but I could be wrong. Yeah, let's, I'm just trying to imagine what's, like, the easiest thing to do here. I want to get more intelligent on this, like, set tracking stuff. So can we do, what are we doing? This is, like, circuits. And then in here, we had these two guys. Right, we have the lookup, which is this, and items, which is this. Oh, I mean, I already know there's a problem here. I already see a bug. So before we get into it, it's when we merge them, we need to go for set items for each thing in the that we moved from B to A. We need to fix their lookup. Oopies. So everyone in set B, when we merge, we need to say lookup. I guess it's like, yeah, set lookup. What fetch put? What is fetch put? Oh, I guess I want like puts, and this just will allow clobber, right? Otherwise, so we look at like index. We set this to a GOP value pointer, I guess. Ew. Stood debug assert that set lookup contains index. I'm pretty sure that that's fine, but I just want to be sure. That's not good. It said my answer was too low when I punched in whatever the fuck I punched in last time. I don't remember what I punched in, but I think that it's way smaller. Okay, let's just get a little bit more intelligent with this circuits. We need to be smarter here. Okay, so we have our lookup, which goes from thing to this goes from like chord index to set index. Then we have sets or circuits. Sets, I guess we'll call it. Which is going to be an array list of usize. No. So this is each set lists all of the chord indexes inside. Okay. So now we can kind of start doing whatever the fuck was happening in here. So it's like, what are our operations here? It's like mark pair, I guess. Like connect. Yes. So this is gonna be A and B. And I need to fucking use I need strong types here because I'm too stupid. So we need like a chord index and set index. And then this goes from chord index to set index. This is chord index here. Okay. Boom, boom. And this is where he's doing like this stuff. So this is like yeah, something like this. I don't know what yet. I don't know what yet. Okay, so then we have this mega if here. And what is this guy doing? Okay, so first, I don't know yet. I'm just trying to make the types line up. So we have like chord index here, which will return something, which will return like, I guess, a chord index to set index, get or put result or something. I don't know yet. Get or put with index inner, like this. Okay. Is this part 2? Dude, I don't think we're even on part 2 yet. I think we're still on part 1. I think I like fucked everything up. I thought it was gonna be way easier than it was. Look up gop. Okay, so now we can do look up gop here. Okay. Then this is what? This is like add to set is kind of what this is doing, right? So we are like yeah, what is happening here? So when we add to a set, this must take a chord index. Okay. And he needs to add to set. So this needs to have like set ID. Yes. Okay, so we have add set and add to set. So add set takes in 2 chords. Right? And that's kind of what this guy's doing. So he says like, and I guess technically, I kind of like the idea of like a lookup handle. Yeah. So we have this guy, we have the like set index in here, which is a pointer to a set index, and found existing. So this is like our like wrapping of the get or put result, I guess. Which is useful for some reason. I don't know what yet. It just feels like it will be. I don't know, man. I don't know. So gop is this. Then we return chord index is gop key pointer. We dereference this. That's fine. Set index is gop value pointer. This might be undefined. And found existing is gop found existing. Now we can pass this thing around easily, which means that like add set can have, you know, lookup handles for both of these, right? So we've done the lookup and we're adding to the set. And now we have like new set index ID is self sets, plural, items len. We do self sets append, an empty thing, and then we say last set, like new set is self sets items at new set ID, and we do new set append, and then do we do add to set like this? Maybe we just do this. Self add to set new set ID. Yeah. Here we go. This is how you keep your shit together, dude. A and B. Oh, easy. Easy. Okay, so this guy takes a lookup handle as well. Oh, this is getting so much nicer. This is getting so much nicer. So then we have self sets at set ID, append, chord index, or this is, yeah, like this, and then we say self, I guess it's like chord set index is equal set ID. Oh, beautiful. Okay, so if we found neither, we're like add set of A gop and B gop. If we did not find B, but we did find A, it's like self add to set A gop set index B gop. If we did not find A, but we did find B, we use B's set index and we append A's gop. And then the last thing is merge sets. And it's like A like this. Yes. Okay, merge sets, which takes in A as a set index and B as a set index. Beautiful. Beautiful. And so we have like a self sets. I already missed the chaos of the initial solution. This is looking kind of structured. Yeah, well, because unfortunately, I got too dumb to handle it. A set is self sets items at A. B set is B. And then we have A set append slice self alloc of B set items. Yep. And then B set clear and free. And then fix me here. I actually want to like recycle eventually, but for now, we just won't do that. We won't do that. Okay, now we're missing the part here where we go for B set before we clear and free. We have B index. We want to do add like update set, I guess, to A. Yes. And update set is different than add to set. So this is my chord is a chord index like this, I guess. And this is just self sets set lookup put chord set ID. And here we can assert that chord already was already in there. You know, something like this. Okay. Now can we try to use this thing? This might still be wrong, by the way, but at least we'll have like something sane to look at. Okay. So now, as we fucking rip these things, let's go back to the example. So we'll do top 10, and we will be looking at day input example. We are doing circuits. Connect. Pair A and pair B. And this is a chord index. Circuits, chord index. Like this. I think it was right. Okay, so now all of this code dies. And then we go for circuits, sets items. Okay. Oopies. Yeah, this guy should be a pointer, so true. Found U size, expected chord index. Nice. Strong typing for the fucking win. Expected void, so these guys don't know how to fail yet, but that's okay. This probably needs an allocator. Probably can fail. This thing can definitely fail, which means that, like, that thing needs to be tried. Okay. 314 is mad because this can't fail, which means that when we connect things, they need to be able to fail here. 291. 291. We just need to be careful about using our strong types here, but here it is. Fine. Okay. Value pointer doesn't exist in 323. Yeah, so this is set index. If they are the same, there's no work today. If they are the same and they were already connected, there's nothing to do. I guess we should probably assert that they are not, though. Maybe. I think this is like a surprising condition. I think. Throw some strong type resolution on there for comparison. So true that we don't want to do that. Expected index found index pointer at 324. Yeah, that's fair. 306 is mad because this is items here. And then this thing is try. Okay, so we are hitting this case, which is probably where the bug is, right? So here we did not find A, we did not find B. So this means that we found one of the two. By the time we get to here, we have found both. And here we are finding both and they're already connected, and that's a shocker. Oh no, but that's okay. That is okay because we might have got there because we connected sets. Okay, so we're back to this working on the original. So now can we bring us back up to the real inputs? And that is a number that we have not seen yet. Let's go! Let's go! Refactoring always works, man. Whenever you don't think your code works correctly, refactor without thinking. Okay? That is the lesson we take away. Always blindly refactor, especially at work. The elves are right. They definitely didn't have enough extension cables. You'll need to keep connecting. I guess we'll write this down. 02, 06, 35. Oops. Part 2. Guys, the lesson is also, for real though, we can't overcomplicate the problems anymore. They're too hard now. This one was way fucking harder than every other one like combined. They definitely don't have enough extension cables. We'll need to keep connecting junction boxes together until they're one large circuit. Continuing the above example, the first connection which causes all the junction boxes to form a single circuit between the junction boxes is between... Wait, the first connection which causes all of the junction boxes to form a single circuit is between... Oh. The elves need to know how far these junction boxes are from the wall so they can pick up the right extension cable. Multiplying the x coordinates of these two junction boxes produces this. Continue connecting the closest unconnected pairs of junction boxes together until they're all in the same circuit. Okay. And then we need to do it in order. Okay, so this is fine. So this just needs to be... I think we're actually so close here, right? It's just the count of the set lookup, right? It's like this is the exit condition is when this contains every single coordinate index, right? So it's like we just changed this for loop. Okay, first of all, git add day8.sig and git commit smiley face. So I think that all we have to do here is this is while circuits set lookup count is less than chords items len. Okay. And then what we want to do is once we connect these, we just say like, I guess actually it's probably better to do this the other way around. I think. So while true here, while true, I think it's like if this is equal to this, break. And now here we can look at the pair distance squared. Or even just the pair. So we say, I guess it's like last pair, we break out of here with pair, right? And then now we can just look at these guys. So we can say we can say A is, I guess we press print. Stood, debug, print. This is chords items at last pair A and B. And let's just see if these look right on the example input. All right. Oopsies. Okay, So we got. Oh, oops. We want to do this on the example input. So he's saying 216, 146, 977, 117, 168, 530. So we got the right answer, and so it's multiplying the x coordinate, right? Right? This is what they said? 25, 272? Let's fucking go. Let's go. Okay, so maybe this is our answer? Boom, baby, let's fucking go. All right. Dude, they ramped up in difficulty. But the final answer isn't that crazy, right? We did a bunch of stuff in here at the beginning trying to do use grid cells or whatever, but in reality, the only thing we actually ended up doing was there's two pieces to this whole puzzle, right? There's the binary heap where we just add items that are sorted by distance squared. All of that is one problem. Well, some of it is garbage, right? So in reality, we kind of don't need any of this stuff. This was our first attempt. But I think the rest of this is one solution. Yeah, this is all used. But yeah, so it's only two parts, right? It's priority queue, easy, binary heap, whatever the fuck you want to call it, something that lets you fetch the smallest item in a list. We compare every single point with every other point, which I think is beatable. I don't think we have to do this. I think the grid solution would have worked if we were willing to put more time into it. I use a heap initially as well, but thinking about it some more, it doesn't actually help much, right? Compared to a sorted list of distance pairs. Yeah, I guess they're the same. Yeah, you're right. We could have just sorted the list the same way. I mean, it doesn't matter. Some way to get a list of, you need to compare all sets of points with each other, sort that list somehow, right? So I used a heap, but you're right. A sorted list is the same. Then the hard part here was this double set lookup, right? So we have list of sets where as we merged guys together, we either have to, we have four cases, right? It's either neither thing was in a set yet, in which case we make a new set. Otherwise, we have cases where one of them was in a set and the other one wasn't, so we add to the set. Or we have to merge two sets, where merge sets is a little tricky. We're not recycling sets right now, which we could have done. But yeah, not too bad. I mean, a lot worse than I expected. Yeah. Have you heard of union find? I learned about it yesterday after this problem. Pretty cool solution. I'll look it up. Union find. Disjoint set data structure. So they do stores a collection of disjoint non-overlapping sets. It's a partition of set into subsets, blah blah blah. What do they do? Each node of disjoint set contains a pointer and some auxiliary information, either a size or a rank. Pointers are used to make parent pointer trees, where each node that is not the root of tree points to its parent. I see. So each tree, you have some sort condition for within a set, so that you have a root of the set, and then everybody points to that parent probably. With members of the set being nodes in the tree, root nodes provide set representatives. Two nodes are in the same set if and only if the roots of the trees containing the nodes are equal. Oh, they're allowing deeper nests though, I think. So because then you can just reparent the root probably, right? So when you're merging sets, you just, instead of having to re-put every guy in the set in the original, you just reparent the last guy. And then also when you're doing your lookup, you don't have to update the lookup pointers either, because you just walk the parent up. Yeah, that is nice. Yeah, that does seem pretty sick. That is better than what we did for sure. Cool. Yeah, I like that. All right, cool. Thanks for watching, guys. If you like what you saw, we stream most days. We're in for 12:34 Pacific time. It is 4:25 now. 4:20 blaze it. Bless up, whatever. we're working on Advent of Code right now because it's fun. We are also working on in Happy Hour we're working on a VLC plugin to automatically track TV for me. We are also working on a Wayland compositor once Advent of Code is over. If you want to see some of the stuff that we're not posting to YouTube, Patreon, YouTube members, Twitch VODs, you support the stream, it continues, you get extra VODs. Yeah, cool. Thanks for watching, guys. YouTube, peace out, and Twitch, let's find someone to raid.